Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Hello, Mike.
Hey there.
I am back from vacation. I was on the central coast of California and in Northern California, where the weather was quite a lot cooler and foggier and more pleasant than it is down here.
Cooler than down here where it's only like 170 degrees. I can't believe it.
Well, it's like about 80 degrees and 80% humidity at my house with really fat raindrops in the morning, summer storms. I don't ever remember seeing that as a kid here, but that's what we get now. We get big, fat summer storm raindrops like in other parts of the country. Mike, I've been listening to a record from a band called Soft Curse. It just came out a couple months ago. The record's called Liminal Ritual. Someone recommended this band, State Faults, to me. They're from Santa Rosa, actually. And they're like, this band reminded me of like late 90s, early 2000s, hardcore, maybe screamo. I never liked that term, but that's what people say. But anyway, they were like, check out our new band. And they described this as gloom metal. And it's pretty good stuff. I was like, whoa, this is like Dead Meadow and Electric Wizard, and there's some Sleep, and there's other rad bands in here. I really like this record. And as soon as I heard it, I was like, okay, I'll just listen to that for the rest of the week. Is that okay?
Yeah, you sent it to me a couple of days ago. I've been listening to it as well. I like it. It's yeah, all the things that you invoked I hear, but also just like more normal doom bands like Paul Bearer, I think maybe a
Mm,
little bit.
mm-hmm, mm-hmm.
Yeah.
They recorded this record in Oakland. The band Soft Cursor from Santa Rosa. I think I was like, oh, cool. Band from California, Northern California. Let's check this out. It's pretty good.
I've been listening to one that one of my sons pointed me at. It's I kind of confess that I chose it slightly because of the title, because it sounds like the title of this album sounds like a good album for a show about software. So the title of the album is called Of Agency and Abstraction.
Oh.
The main performer is a person named Rajna Swaminathan.
Hmm.
So I apologize for most likely butchering that, but she's primarily a percussionist. And
Hmm.
so the I guess you would call this album jazz. It's got some vocal parts too that are from some Indian singers who are apparently pretty well known, but I had not heard of them.
Oh,
Um,
from Bollywood singers?
no, I don't think. I think it's like more classical Indian
Oh,
vocals,
okay.
but in any case, yeah, it's really the kind of the percussion parts that are interesting. She plays redangam, I think it's called.
Mm.
Just kind of interesting drum that plays different tones and things. So there's like elements of Indian music and elements of traditional jazz, and it's kind of interesting to listen to.
That sounds cool. I'm gonna listen to that. Of Agency and Abstraction. I always love the tabla. Tabla to me has that boom sound,
Yeah,
like water dripping into a puddle in a cave.
yeah, exactly. Yeah.
It's a beautiful sound. So, friends, if you'd like to reach out to us, you can find us on Blue Sky under Picture Me Coding. And you can also send us an email, podcast@picturemecoding.com. And if you like what we're doing and like to support the show, we do have a Patreon for $4 a month. You can help keep the show on the air. Can we say that on the air? Do you say that with podcasts? I don't even know if you say that.
Yeah, I mean they're like going across like wireless Bluetooth.
Go,
So
going across the radio waves, going across Wi-Fi. That counts, right? Radio waves beaming out into the night sky. Anyway, we have a Patreon for $4 a month. You can help support the show. We use that to pay for hosting costs and other things. We appreciate our Patreon subscribers. Thank you so much for helping us put on this show. Mike, I just got back from vacation, so we haven't recorded for a few weeks. One of the things I did on vacation, we were in San Francisco in Golden Gate Park. There's a lake in the park, not the fly fishing lake, not near the bison or the windmills. This is more toward the guts of the park. I always called it Stowe Lake, but apparently on the maps, it's called Blue Heron Lake. It's over by the Academy of Sciences building. Do you know the lake I'm talking about? There's a funky island right in the middle of it. Have you ever seen that in Golden Gate Park? The water is green.
I have probably seen it, but also did not know what it was called.
Well, we always called it Stowe Lake in my family, but that is not what it's called on the map. I have no idea what it's really called. I don't know why we called it Stowe Lake. Maybe that's the old name for it. Anyway, I rode around in one of those paddle boats where you pedal with your feet with my son, and we paddled around. And we were like, oh, this looks so easy. Look how slowly these people are going. We swim multiple times a week. We're gonna do like 2 or 3 laps around the lake by the time our hour is done. And we really only did 1.5. First, because by trying to go very fast, we exhausted ourselves. I was actually sore afterwards paddling one of these. I've never done this in my life, a paddle boat. And the second reason was we saw this nest of baby birds. We just sort of sat there watching the baby bird. So the baby birds foiled our plan to go 2 circuits around Stowe Lake. Anyway, paddle boating. It's kind of a was kind of what I was fun thing I was doing. We also went tide pooling and hung out on the Central Coast a lot. While I was away, you were here, though, furiously working on the next episode of our show. Is that right?
Yeah, furious might be a little bit of an overstatement. Um,
Lackadaisically working on
I
the
was
topic you wanted to cover today. And I was like,
persistently, but slowly working on the next episode.
you said to me, hey, are you up for talking about this? And I said, yes, maybe I will finally understand it.
Yeah, well, I think that's a little ambitious, but
It's not going to happen. I can tell by the document. You wrote this document together. I'm like, I still don't get it, but I get pieces. So you want to talk about Monte Carlo method? I also thought it was Monte Carlo methods. There's like a cluster of methods. We just say one method, Monte Carlo.
yeah, it's some people also call it the Monte Carlo algorithm, but it's really not just one thing. It's sort of a collection of tools, but
Mm.
I think it's interesting both because it has sort of sort of an important place in the history of computing, and also it's something that I've encountered a few times in my own career. So, and it's not AI. So,
Oh, that's a plus right now. Not AI. Not that we hate AI, but you get a little tired of it. If do you not get a little tired? I get a little tired of it.
it does have a small place in the AI world, at least one that I know of, which is in things like chess programs and Go programs, where you have to, at some, like if you're doing reinforcement learning, there's a stage where you go through a tree to look at all the possible next moves you could make.
But exhaustive enumeration of different moves is maybe huge, huge state space, right?
Yeah, exactly. And so there's this thing that people started using at some point called Monte Carlo tree search, which is maybe make more sense after we talk about this a little bit. But in any case, there is a there is a tenuous AI connection there.
Okay, so you already gave a clue there. So Monte Carlo, if I'm searching around for answers within a massive state space, I can potentially use this thing to do that. Is that a fair, like very, very explain like I'm five?
Yeah, I think that's a good place to start. The idea supposedly started with a physicist, a mathematician named Stanislav Ulam. He was one of the people involved with the Manhattan Project.
Mm.
I think either during that time or maybe after that time, he was in the hospital for some reason. And this is the way the legend goes anyway. And I think it's probably been repeated enough that it's pretty close to the truth. But
Hmm.
um, he was supposedly in the hospital and he was playing solitaire. And I one problem with this particular explanation is I'm not exactly sure how you play solitaire. I know it's a card game that you play by
You
yourself.
never, you never played solitaire?
I'm not sure that I ever have, or if
Oh,
I have, I don't remember exactly what the mechanics of it are. But in any
you have to
case,
make runs of numbers.
yeah, my understanding is that you sort of shuffle the deck and then you go through this process of making runs of numbers, and sometimes you are successful at it and sometimes you are not, and so
Hmm.
the game sort of ends without without a conclusion.
Hmm. Hmm.
And so Ulam started to think about like how likely am I to get a successful outcome when I'm playing a game of solitaire.
Hmm.
And he was being a mathematician. He realized pretty quickly that the total number of possible arrangements you could have is astronomical.
Because
So
52 cards.
yeah, And so, like, literally enumerating all the possibilities was not an option. And so he kind of hit on this idea that if you played enough games, you could count the number of successes you had out of the total number of games.
Mm-hmm.
And, so maybe you play 1,000 games and you keep track of how many times you actually reach a conclusion.
Mm-hmm.
And his idea was that by looking at that percentage of successful plays, you could get the more games you played, the more close you could get to a good approximation of the probability that you would be successful
Yeah, and
playing a
so it
game
is.
so
It's
often.
a ultimately talking probabilities. We're talking ratios here, right? Like how many times am I going to win out of total So there's a ratio involved. There's a probability involved.
Yeah, and that comes up a lot in the when these methods are used for real computations.
I tried to read the original paper they published on this. Couldn't read it. Couldn't understand it.
It's not too bad. I think you do have to kind of understand the place they were coming from to a certain extent. So one thing that's kind of interesting, but maybe slightly disturbing about the development of the Monte Carlo method is that a lot of it was motivated by the attempt to build a hydrogen bomb.
Mm.
So after World War II, the Russians got the atom bomb, and so we were kind of compelled to come up with something even more deadly. Whether or not that was a good idea still remains an unanswered question. But there were a couple of physicists who really were pushing this idea of building a hydrogen bomb, particularly Edward Teller.
Mm-hmm.
And so they kind of repurposed the weapons lab. So one of the papers the original paper on this method that was written by Ulam and a guy named Nick Metropoulos, who kind of led the computing efforts at Los Alamos. They talk about the method in general. They even talk about the solitaire case, but a lot of it was motivated by experiments that they wanted to do related to uh, figuring out how to make bombs explode, nuclear bombs explode.
Hydrogen bombs, massive bombs.
To set off a hydrogen bomb, you have to have a pretty significant explosion of a conventional fission bomb.
Mm-hmm.
And so they were trying to basically figure out ways to make the fission part of a nuclear explosion more powerful than what they had been able to do with the bombs in World War II. So let me read a passage from the paper that kind of describes what they were trying to figure out. So this it says, finally, let us consider more generally the group of problems which gave rise to the development of the method to which this article is devoted. Imagine that we have a medium in which a nuclear particle is introduced capable of producing other nuclear particles with a distribution of energy and direction of motion. Assume for simplicity that all particles are the same nature. Their procreative powers depend, however, on their position in the medium and on their energy.
Procreative powers depend on their position in the medium. And so, like, how much explosion you're going to get is based on where the stuff is and how much energy it has. So there's like a lot of possibilities.
Yeah, there's a lot of possibilities. So this neutron comes into the material and maybe it hits something and it splits off. It fissions and causes two new neutrons to split off, and they go off in random directions at random velocities, and
Mm-hmm.
maybe they split again. And so what they were trying to do is essentially do a bunch of experiments to see what the best materials were, what the best arrangement of materials were, so
Mm-hmm.
that they could get the most efficient fission. And the problem with doing this experimentally was you didn't want to use up a lot of uranium or plutonium doing experiments to verify your theories. So they invented this method that they knew they could experiment with on computers.
You just take a bunch of samples and then you see how likely it is based on whatever your setup is. This is my very dumb and as description of it.
Yeah, well, there's certain parameters that they could change, and then they
Mm-hmm.
could run these simulations over and over again, and they could essentially, do this thing that they were describing over and over and basically collect statistics on how the process evolved.
In the paper they write, imagine that you have like a 20-term polynomial and you're trying to figure out, I guess, a reasonable answer or set of answers, right? That's sort of one of their motivating. And I sort of always in my head think, okay, so they're like nuclear fission material thing is something like this. Like it's this massive
Well, yeah,
multi-term polynomial.
that particular example that they gave with the a function of 20 variables, they're they're actually trying to describe essentially computing the volume of something in a very high dimensional space.
Oh,
And
okay. So I missed that. Yeah.
this is something that comes up a lot with the Metropolis method too. Is that a lot of times what you're effectively trying to do is an integration. So,
Hmm.
and as you learned in calculus, like area under the curve type of stuff, except usually in many more dimensions. And the problem is that very often the processes or the things that you're trying to simulate are not things that you can easily integrate analytically, and so you can use these methods to sort of get an estimate of the correct integral.
Hmm. Now you've actually worked with Monte Carlo methods. You brought it up to me a long time ago, and you recommended a book to me, which I still own today, called Probability in Computing. When did you first encounter Monte Carlo methods?
So looking back on it, I think the first place where I encountered it was probably in high school, and I don't remember the
I don't know if that
context.
makes any sense. You found it. I didn't encounter this in high school.
I was so incredibly cool and popular in high school um, because of all the math and puzzle books that I like to read. You know,
Oh, okay, okay.
like like most cool popular people. I was really into math books and mystery books and things like that. Um, but I remember coming across this. It wasn't described this way, but it turned out to be an example of what people call Buffon's needle problem.
Hmm.
And I think the way I came across it was there was this person and they were like dropping matchsticks onto the deck of a ship,
Mm-hmm.
and it it came up that by doing that you could estimate the value of pi.
What?
And,
But isn't it like you drop them and then if they cross, so you imagine you've got a wooden chip and you got a bunch of floorboards and there's seams between them, right? There's lines where the
yeah,
boards meet boards. So it's like when you drop them, what's the probability that they cross a line? Is that right?
yeah, that was actually what Buffon was originally trying to figure out. Is just like how probable is it that this needle in his case was going to cross one of the seams between the boards.
And
And
I didn't know this was related to pi. That's crazy.
yeah, it turns out, especially if the needle or the matchstick is if the length of that is less than the width of the board, it's actually there's it reduces to a pretty simple formula. So if you just drop the match or the needle and you count the number of times it crosses one of the seams compared to the total number of times that you drop it, you can get closer and closer to an estimate of the value of pi, which is essentially what the a very simple case of what the Monte Carlo method is often used to figure out.
Yeah. In the book, in the probability and computing book, they have this motivating example to start the chapter about pi. And I read that example and I'm like, well, that makes a lot of sense. You have this unit circle and you just sort of pick values sort of near the unit circle and then you calculate whether or not uh, like it's a hypotenuse of a triangle, you calculate whether or not the x and y end up being the Pythagorean theorem, it ends up being less than or equal to one, and the probability you end up with is pi. It's like, okay, that makes a ton of sense. How the hell do I use that? I kind of can just plug in pi. I don't understand this method applying it to other problems.
Yeah, I think that's the second place I encountered it too. Was I worked for this guy when I was an undergrad in college, and um, we were. I was talking about something in his lab, and he said, "Well, you could use the Monte Carlo method," and I was like, "What's that?" And he gave me this example of calculating pi or calculating the area of a circle. So the like you said, what you do is you have this square. Um, I've seen it set up. I've seen it described a couple of different ways, but the way they describe it in this book is you have a basically a two by two square that's centered at the origin, and then inside that you have a circle with a radius of one. That's where the center is right at 1 1,
Mm-hmm.
and then you pick random you pick a random x and a random y uniformly inside the square, and you compute the number of times that that random thing is inside the circle versus the total number of random points that you pick. And
You said the
again,
center of the origin of circle is at 1, 1. Isn't the origin of circle at 0, 0 in that case?
well, you have to do it. You have to do a little bit of a transformation. The other way I've seen it set up is you just have like a quarter circle. So
Mm.
you have a square that goes from one on the x-axis and one on the y-axis, and you
Mm-hmm.
just have a quarter circle inside there, and you can do
Inside the
the
square. Inside the
inside the
square, right?
square.
Okay, right. So now you're randomly picking values. Is it in this quarter circle or is it outside the quarter circle?
Yeah, and it's very similar to, again, like doing a an integration, because
Mm.
you're effectively trying to find the area under the curve.
This is one of those things though that's like that's a deceptively like I hear this or I read it in this book and I go, "Oh, that makes a ton of sense." But I absolutely have no capability to apply this to any other problem that's not estimating the area of the circle.
You can sort of extend that to doing other types of integrations.
Well, I could see that makes sense, but you had a couple of other examples in your career where you had to use Monte Carlo for something, or maybe didn't have to. You just wanted to because it was way more fun.
No, I think there were cases where we had to. Yeah, as I mentioned, I think on this show in the past, the first 15 years or so of my illustrious career was doing simulations, mostly of molecules and systems of molecules.
Hmm.
And there was one point where I was working with a guy who he worked on what were called polymer crystals, which is kind of a puzzling thing because polymers are usually amorphous, but apparently there are some situations in which polymers will form a type of crystal.
Hmm.
And it was something that was relatively hard to simulate with normal like dynamics methods. And so we had set up this thing where basically you take a couple of polymers that were kind of like rigid chains, and you pick a configuration at the start and calculate its energy, and then you'd move it in a certain way and calculate the energy of this new position. So two things could happen. One is that the new position that you've picked could be lower energy, in which case you're good. You just keep that one. The other possibility is that the energy actually goes up slightly, in which case you check the energy against something called the Boltzmann distribution, and you can determine, given at a particular temperature, you can determine what the probability is that the energy of this system would go up by that amount. Um,
So you could
and
kind
if
of
it
rule it out with the Boltzmann distribution.
well, what would happen is you could pick some probability level and say, okay, I'm gonna if the probability that this transition will happen, to, if the probability that the transition to this new energy is relatively low, I'm going to keep it.
Hmm.
But if it turns out that the probability of switching to this new energy is pretty unlikely, then I'm going to stay where I'm at and then pick a new random configuration from that.
Okay. Okay. All right. All right.
And this this method in general was what came to be called the Metropolis Monte Carlo method.
Hmm. Every time I
So
ever heard Metropolis Monte Carlo, I always thought Metropolis. You mean like a city, like finding highs and lows, like local minima and global minima, right? That's like buildings, skyscrapers. No, it turns out Metropolis is the person Metropolis. What a what a rad last name. For some reason, I cannot ever remember it's a person. I hear Metropolis Monte Carlo, I think City Skyline.
Yeah, it's confusing because Monte Carlo is sort of an arbitrarily chosen name that was kind of fun because it involved this random component. But Metropolis is actually the name of a person
Hmm.
uh, that we've already mentioned. But
But the Metropolis thing, is that the Markov chains where it's like you're repeatedly sampling from the likely distribute from the likely historic. I'm
yeah,
gonna not say this well.
yeah, that it's an example. It's Metropolis Monte Carlo is a version of what later became known as Markov chain Monte Carlo.
Hmm.
So Nick Metropolis and Ed Teller and some other people published this paper. Can't remember what year it was. I think it was early 50s. They published a paper, which again was a result of their work on the hydrogen bomb. They published a paper that talked about using this method, and because Metropolis was the main author, it later became known as the Metropolis Monte Carlo method. But a couple of decades later, a guy named Hastings published a paper that was basically like a generalization of this method to any Markov chain, and that became known ultimately as Markov chain Monte Carlo.
Oh,
But
okay.
yeah, it's called Markov chain Monte Carlo because a Markov chain is this thing where you're making transition from one state to another state, but the state that you transition to is only dependent on the state that you're currently at. Um, so
And it's governed by probability, right? It's like
yeah,
you don't know deterministically where you're going. You're going to make a probabilistic transition to a different state.
even the original like neutron simulations they were doing at well, they were doing them on the ENIAC. They were doing them for Los Alamos, but not at Los Alamos. I'll just say
Hmm.
for now. They were essentially kind of a Markov chain Monte Carlo because there were certain probabilities that a neutron would fission, and so that's you can sort of view that as being like a transition from one state to another state.
Hmm. So you've used this in your career. What's the 5 minute? Here's how you use it thing you can pitch me on. We give it to our listeners. Say, listeners, here's how you want to play with these. This is how you do this.
Yeah, so it's very difficult to boil down to one thing. So I will say, like you and I worked at a company for a while also where we used a variation of Monte Carlo, which was basically trying to estimate what the returns from a portfolio of stocks and bonds would be after like a period of say 20 years.
Hmm.
And this is another case where it's not like the previous case I was talking about where there's like energies involved and real physical properties. It's mostly stock returns that you're basing on like historical returns and stuff. But the sort of common elements are that you're using some sort of probability distribution to pick new configurations of things, and you're also trying to repeat this process enough until you get a decent distribution of things at the end that you can compute statistics from.
Can I just say, when you first told me about this, I thought, well, that's confusing because I could just run, random number generators across stocks all day long. And how do I know that any particular set of values is any more useful than any other particular set of values, or more likely, I guess?
So it's not just random numbers. It's random, but it's from a particular distribution. So in the case of in the first case that I mentioned, you're looking at physical things in a like say like particles in a box or something that
Hmm.
are subject to certain temperatures and pressures, and you know we know from physics that the things in there are going to take on a certain distribution of energies,
Hmm.
um, and that's governed by the Boltzmann distribution.
And there's well-defined bounds, I guess you could say, well-defined max and mins and stuff.
You know that certain energies at certain temperatures are going to be probable and certain are going to
Hmm.
be improbable, and some are so improbable that they will not actually be reached. And so it's similar with the stock case. You're not simply choosing this you're not choosing a random number that says, okay, this stock is going to have 100% returns this year, or it's going to have negative 100% returns this year. It's usually based on, say, the history of the returns of a particular stock, and
Hmm.
maybe like macroeconomic factors or other things that you factor in there. But the idea is that with a stock case in particular, if you have like a portfolio of stocks, you don't know what the returns are going to be, but you know that they're going to probably follow a certain distribution. If you look at various time periods and pick the returns for the portfolio at that time period, and you simulate that over like say 20 years, and then you just repeat that over and over and over again, at the end you will get a whole bunch of different outcomes, but those different outcomes will have a distribution that sort of tells you whether or not the things that you've chosen in that portfolio are a decent set of things to have chosen. Um,
Okay. I think I get it. I mean, it still is confusing to me because if you said to me, hey, I'm just going to pick a bunch of random values for a particular stock, right? And I would say, great. Isn't the ultimate answer, if you do that enough times, just going to be a regression to the mean of whatever your distribution that you're picking random values from, right? If you could pick 0 to 100 and you pick enough times, probably you're going to end up with 50. But what we're talking about is that there's a lot of stocks, different parameters. There's a probability distribution based on historical performance. It's a little more complicated than just picking numbers out of a hat.
yeah, so this is like over a portfolio. So you have a number of securities, and they may be stocks, they may be bonds, things like that, and they will have some correlation between them. So
Mm-hmm.
when you're picking the random the random values that you apply at a particular time period, they are somewhat dependent on each other. There's a sort of a covariance between them. So, like you say, if you just have a historical return and then you simulate that historical return into the future, you're just going to end up with a mean that looks like the the return that you've had historically. And
But can I
um,
throw in arbitrary variables? Like, let's say the possibility that I get a bankrupting illness in the next 20 years. Can we put that one in too as a variable?
people do that, and people try to do like forecasting into the future where they may make assumptions about how the overall economy is going to behave. So,
Wow.
um,
And the
you might,
nuclear Armageddon clock gets to 0.
yeah, I mean, these things can get pretty sophisticated if you add enough if you add enough potential factors into them. But again, they're all sort of dictated by um, some sort of probability distribution.
So giant state space, a lot of parameters, trying to predict values for these parameters and then figure out what the most likely answers are after you've picked enough. In the probability and computing book, they have once they get beyond the circle, you read the circle like I did, and you're like, cool, okay, I get it. What the hell does that apply to anything I've ever worked on? The circle example. I don't really want to compute pi myself. They have good content in the chapter following, but it's got too many lemmas and proofs for me. So I get like the further the chapter goes, the more lost I get, Mike. But they give this example which I like, and they're talking about they give the example of a disjunctive normal form formula. So it's a satisfiability formula, right? Disjunctive, disjoint, or, right? So if I've got a bunch of statements in a satisfiability problem, I've got A and B and C, or whatever, D and E, or, and you can imagine parentheses in there. So that's disjunctive because it's the statements are ored together. And or disjunctive sounds a little bit easier to try to evaluate quickly because if you have or, you want to know if it's satisfiable. You want to know if you have an answer for if you assignments for these variables that ends up resulting in a true for your formula. Because it's disjunctive, it's the first or the second or the third. You could just any one that's true, boom, your formula is satisfied, right? So that's a little easier than doing conjunctive. And they said it in the book. So they're like, okay, we want to count the possible assignments in a disjunctive normal form formula. So we're going to try to count, but you can't count it because the number of possibilities is massive, like these other problems we've been talking about. So they use this as a motivating example for Monte Carlo. So it's like, okay, cool. We could just start pulling random assignments for A, B, C, D, whatever, how many variables I have. We can plug them in. That's great. They end up calling this the naive approach because you you may end up having so many there's like a cardinality explosion, right? Like you might have an exponential pursuit or search for these of your sampled assignments. They have this line that I really liked. So they're like, the problem with this sampling approach, just sampling randomly. The problem with this sampling approach is that the set of satisfying assignments might not be sufficiently dense in the set of all assignments. So I really like this statement. It makes a ton of sense to me, but it immediately leads me to more confusions and more questions. So how do I know I want to pick random values, but I want to pick good random values. And if I have an awareness of quote unquote what a good random value is, if if I already know where the answers I want to be are likely to be hanging out, then don't I already kind of know the approximate answer?
So I think this is saying kind of the opposite thing, which is that you don't know where they're hanging out. Um, but
That's
if
what I thought
you
Monte Carlo was about. You're trying to figure out where they are.
yeah. So what they're saying in this problem in the book, I think, is that if you do this the naive way, so there's going to be assignments that satisfy the problem, and there's going to be assignments that don't satisfy the problem, and you pick them randomly.
Mm-hmm. And
And
then just to restate the problem, it's possible that the assignments that don't satisfy vastly outnumber the assignments that satisfy. So if you just start picking randomly, you could be picking for a long time.
yeah, so that's what they're trying to say is that if you do this the naive way and you pick from a fairly what seems like an appropriate but simple distribution, the satisfying assignments are going to be so rare that you basically are not going to find any unless you run this for a very long time. And to get enough of them that you can get like a statistically useful count, you're going to have to run this, and it's going to be exponential. The amount of time that you're going to have to run this for is going to be exponential in the number of terms in the
Mhm.
thing you're trying to satisfy. So the what they go on later in this book to talk about is how you can sort of pick a better distribution so that
Right.
the the satisfying assignments are more dense in that distribution.
So that problem makes sense to me. And they're like, well, we want our search to be polynomial, meaning we want it to be bounded. We don't want it to go on forever. I don't want to run this program and come back and check 2 days later and say, is it done yet? And will it be done this year? And will it be done before the sun burns out? W- We want to search in such a way that we can get a decent answer. Um, but that's the problem. That's what I didn't understand. They move on and they're like, they have a lot of lemmas and proofs, and then they start talking about Markov chain Monte Carlo. How do you, and the quote from the book is, sample from the appropriate space? How do you do that?
I think what they do in the book, and again, I'm kind of winging this because it's been a while since I read it, but I think what they do in the book is that they essentially try to look for um, satisfying assignments of individual clauses in the thing that they're trying to satisfy, and they kind of construct a distribution of things where satisfying clauses are much more likely to be, or satisfying answers are much more likely to be um, dense. They kind of touch on this in the original Ulam and Metropolis paper where they're talking about the 20-dimensional volume. So they talk about trying to calculate the volume of this area of space which is in 20 dimensions, and they talk about how it can't be vanishingly small, meaning that when you're choosing random values in this 20-dimensional space, you want to make sure that the number of points that you randomly choose, there's a fairly high number of them inside the area that you're the volume that you're trying to calculate, because Otherwise, you're going to run the simulation forever and not find enough points inside that
Hmm.
volume.
Hmm.
And so that's the that's effectively what they do in the book is they sort of contrive a new distribution where the satisfying assignments can be proved to be more dense than they would be in the naive approach.
So I never did statistics. I never took statistics. I've never tried to claim to be any good at statistics. And in fact, contrary to, I usually tell people I'm terrible at statistics and probability. The only distribution, the only two distributions I could tell you about with any sort of fluency is the uniform random distribution and the normal distribution because I could just sort of draw those. Right? So uniform randomness, I get that. That's what I use the word random for. And normal distribution, I get that. But it feels like with these Monte Carlo methods, there's an art and a science to picking a distribution that's maybe not necessarily one of the ones I just mentioned. I mean, the example you gave up above with the polymers was this Boltzmann distribution. There's like this knowing what's a good set of values to sample from to pull numbers out of your hat. The shape of the hat seems to matter here. Is that right?
Yeah, and I think this is one of the benefits of what they call Markov chain Monte Carlo. You're giving yourself a better chance of getting decent samples. Um, the Markov chain stuff was like really popular maybe 10 years ago, kind of
Mm.
before deep learning broke everything, um, because it's very useful in Bayesian statistics. So you could use it to you could set up a fairly simple prior distribution and then run the simulation using Markov chain Monte Carlo, and the posterior distribution that you would get might be really complicated, but it was going to be a distribution that really well reflected the actual problem that you were working on, and
Oh, it's
so
bespoke. Yeah.
bespoke, yeah, bespoke distribution.
Yeah. It's a bespoke distribution. Now, Monte Carlo methods for you, it's not just this abstruse mathematical statistical thing that you're interested in. Like for you, I mean, this is a question that I have is like, okay, but how do I write programs? Do I use this in programs? And you were like, yeah, this is like, it's got sort of deep connections to the history of programming.
I think this is what really interests me about Monte Carlo, more so than the method itself, is how important it was in the early days of computers. You know, in the 40s, there was this group of people developing the ENIAC computer. I think it was University of Pennsylvania. You know, they needed funding, just like now, where people need to get money to work on their projects. And so one of the things that they sort of proposed was that they could use this computer to help the military create what are called like firing tables or ballistics tables, which they could use to like fire their guns.
Nice.
And
Blowing stuff up again. Math and
yeah,
service to blowing things up.
yeah, and so the ENIAC was associated and actually I think located at what was called the Aberdeen Proving Ground. They didn't really, get to the point by the end of the war where they were using it for that, but that was kind of like the first application was these firing table type things. But probably the next thing to be that they used the ENIAC for was these Monte Carlo calculations. One of the interesting things about it was that it was during this period in like 1946, 1947, where they were kind of changing the way that they programmed the ENIAC. So when they first built it, the programming was like this really complicated thing that actually involved like plugging in cables and moving around switches and hardware components and stuff. And around this time, they were kind of trying to reconfigure that so that they could program it using what they called the stored program approach, which is still basically what we use now.
The von Neumann architecture, right? The von Neumann
Yeah,
thing.
this would
Like,
lead to what was later called the von Neumann architecture and the EDVAC computer.
mhm.
The Monte Carlo simulations, which again were primarily focused on these fission problems. They were devised by Metropolis and John von Neumann and some other people to run on the ENIAC, but They were one of the first ones to use this sort of new approach to writing programs. Another thing that's always been really interesting to me was that a lot of these what were called programmers in those early days was actually this group of women. And if you search this, you will find like this group of six women who were basically the original programmers of the ENIAC. The theory has always been that these men who were physicists and mathematicians felt it was like beneath them to actually work with the machine.
Hmm.
I don't know how much of that is true or not, but because a lot of these women were also like very well educated. Like the woman who kind of led this group of ENIAC programmers actually had a PhD in physics herself, so it's not like she was just running a calculator or something. After kind of devising the approach to these Monte Carlo codes, one of the people who did a lot of the actual work was John von Neumann's wife,
Oh,
uh, who was her long name was Clara Don von Neumann, but usually she was either called Clary or Clara. She was really the key person to write these programs, these Monte Carlo programs that were used on the ENIAC. And I don't know, I find the whole story of her doing this work and running these simulations on the ENIAC to be kind of fascinating.
you told me a story that she was married to a guy named Carl Eckert after John von Neumann, and I was like, "Oh, I recognize that name. This is like there's a building at Scripps Institution of Oceanography named after him."
John von Neumann it's a well-known story, but he died fairly young. He, I think, had cancer and died when he was in his 50s, maybe. Um, and it was not too long after they had done this work, and then she married this guy, Carl Eckert, and moved to our neck of the woods
Hmm.
because he was an oceanographer who I assume worked at Scripps Institution.
Yeah,
Um, so
pretty influential that they named a building after him.
yeah, so yeah, she moved to La Jolla. She wrote these programs, and the resource was pretty scarce. So it wasn't like, first of all, she couldn't like, prototype them on her laptop to make sure they were right. This was stuff they had to like flowchart. And there's a there's a part where it talks about a code listing that was written in Clara von Neumann's handwriting that was 28 pages long
Jeez.
and had like little notations in the margins where she was like tracing through the code to see how it worked.
Can you imagine
But
writing all that stuff without ever running it to know if each little piece is going to work, and you know that you're going to have people walking around a room and looking at vacuum tubes to actually evaluate this program, and you just kind of like, all right, I hope I don't look embarrassingly bad in
yeah,
this.
it had to be super stressful. I mean, she first of all, they talk about they really only had 3 runs on the ENIAC computer to do these simulations, and the first one was kind of like a dry run to make sure that all the stuff, all the bits and pieces worked together,
Hmm.
and and then the second one was kind of the second and third one were kind of like the main calculations. It's not like they could like run them and debug them and fix some lines of code and then run them again. It was like you got to run, and it either worked or it didn't work.
Mm-hmm.
And this was still the era where they were feeding in punch cards,
Hmm.
and the the capacity of the computer was small enough that a lot of times they would have to like feed in a punch card to start the computation, and then the computer would write out a punch card or another set of
Uh,
punch cards, and you'd
hmm.
have to take those punch cards and feed them back into the computer to restart the simulation at a new point. And so, anyway, it sounds super stressful. And, she was trying to justify these to people like Metropolis and to her husband and Enrico Fermi, you know, Nobel Prize winners and stuff like that. So it's just sort of a fascinating story.
So it's interesting. So Monte Carlo methods they go all the way back to the beginning of running programs on computers, and I had no idea that that was the case.
Yeah, like almost literally among the first programs and some of the milestones. Like we said, it was kind of like one of the first store to program computer programs.
Hmm.
it was the first use of a pseudo random number generator.
Mm-hmm.
So, they had to have this random aspect in these programs. And so John von Neumann kind of invented the pseudo random number generator.
Jeez.
And it was also so possibly one of the first programs to use what at the time they called a closed subroutine.
Hmm.
So, which is kind of like what we would think of as a subroutine, like a chunk of code that gets called repeatedly and compute, uh, you know, the same thing with different parameters.
I don't use the word subroutine for that, Mike. I usually call that a function.
Yeah, I know, but hardware people call it a subroutine. And
Oh, okay. Yeah. If I
they,
read the C programming manual or I read the history of Linux, I use the word subroutine. And I'm like, okay, old people, I'm okay. I'm with you.
well, I mean, Data from Star Trek is still using it in the 24th century. So
Oh, he
it's,
used subroutines. I
yeah,
never watched Star Trek.
he
I
has
guess I watched the
subroutines.
original.
He has subroutines in his brain. So, you know,
Oh, wow.
it's still a
Interesting.
thing.
So he's running COBOL then. That's what you're
Yeah.
telling me.
It was also apparently one of the first programs to use a loop for something that wasn't computation. So
Huh.
there was like a there was like a lookup table, um, and so there was like a loop or like a set of loops that would go through this lookup table to pick out particular values, and it was one of
Hmm.
the first programs to ever do that.
Here's a question that may be tough to answer. If you don't use Monte Carlo methods directly, are there common applications of them? Like if I go on to some website or I look at mapping software, whatever, I don't know. Is it likely that there's Monte Carlo methods involved in some application that we use regularly, or is it you don't know?
Used regularly, I don't know.
You gave the example of weather forecasting, but that was one of the Clara von Neumann's things.
Yeah, John von Neumann and Clara von Neumann also did some of the first weather simulations. I would guess that there are probably still some Monte Carlo elements to certain parts of weather simulation. Like I mentioned earlier, I know it comes up in game playing. Um, it does come up still as just like a statistical method for um, doing analytics. Although again, I think it's still an important method. I just think everybody starts with neural networks now. So
Hmm. I don't think I would start with neural networks. I opened a door to my house last night and just let the cool air come in. Normally, we open our front door and our dog just barks like crazy. So, what I need to do is calculate the probability that I open the front door and the dog doesn't bark based on whatever parameters there were that I was seeing last night. I don't know what those parameters were. Maybe we could help. I could use Monte Carlo to figure those out.
just keep track of how often your dog barks and also know the entire state of the world.
Yeah,
So
temperature, humidity, wind speed, who's walking outside.
our dog was barking, oddly barking one night recently, and the next day somebody told me that there was a big lightning storm in the East County of
Whoa.
San Diego. So my dog can apparently detect lightning. So
Wow, that's a cool power.
got that going for me.
So, Michael, I feel like I understand more about Monte Carlo methods like abstractly, as kind of academically a little bit, if that's fair to say. I couldn't use them, I don't think. I might be able to look at a problem and go, oh, that looks like potentially a candidate for Monte Carlo.
I think you could use them. I think it's just sort of a matter of internalizing them a little bit. I
Oh, it's
mean,
one of those, you just have to build it and you get it type of things.
yeah, I mean, they can get pretty complicated, but also this is sort of meant to be a method which is simpler than the alternatives.
Don't
So
compute it. Just stupidly pick a whole bunch of random values and let's see what you get.
no, you intelligently pick a whole bunch of random values and see what you get.
Well, I use the word stupidly because what I want to do is do pip install the library that picks the distribution for me. Picks just maybe it's Markov chain, whatever. Just feed me random numbers and then I'll see what happens. That sounds great. I could do that. I'll write that program. Trivial looping, Mike. Well, thanks for taking me on a tour, Monte Carlo methods. I enjoyed it.
I don't know if we enlightened anyone, but I think it is important to know the the historical place these things have and how important these methods were especially during the 20th century.
And you know what? We missed the real sales pitch. Listeners, you will predict the stock market with this simple tool, right?
This one weird trick.
This one weird trick, and then you will know the future. Well, this has been Picture Me Coding with Eric Aker and Mike Mull. Thank you, as always, for hanging out with us, and we will be back again in a couple of weeks.
See you next time.
Bye-bye.